Record. Hey, recorded morning and afternoon class. What a day this is. All right. Got people stumbling in from lunch, so that's good to see. Welcome, everybody. So, what we're going to talk about today is the types of requirements representations that we have. So, today's kind of a high level. We're going to go over some of the different types of, cooking a grilled cheese. Snazzy. Multitasking. I don't know if any of you saw or if any of you are Red Wings fans, but there was a news story yesterday. They were having the draft interviews, and they're asking Yzerman why he was muted and screen off. He's like, "Well, I was doing yoga while you were all interviewing people." Oh, that's awesome. Ah, good stuff. Top dog doing yoga while you have your important questions being fired at 18-year-old draft picks. Alrighty, so I hope it's a good grilled cheese. So we're going to go over the different types of models that we have to take our requirements and move them to something more kind of easily identifiable by everybody in your team. And then next week, we're going to start going into the nitty gritty of how to actually create these models. So today, you get the high level. We'll do some discussions as we go, and should be fun in the bun. And with hopefully a decent little demo of a use case diagram. Got a little Wacom tablet here. It's was acting up in the morning class, so hopefully it's not as painful for you all as it was for them. But let's start off with your in-class assignment from last time. Excuse me. So definitely appreciate the attempts at requirements that you all did. Obviously, I only gave you, 10 minutes to come up with a handful with very little structure or instruction on how to do them, other than my high-level guidelines. But what I kind of want to do right now is I picked some of them that you all submitted, and I would like to constructively critique them, so to say. So the points were entered, so if you participated, you should see points by your name. But kind of the goal here is to go through them and see where we could improve these, basically. So first and foremost, your NFRs and your FRs. Again, NFRs are going to be your quality related requirements, right? They should still be measurable, but it should be maybe something to do with presentation or performance, right? Things that are a little more harder to quantify. Should still be quantifiable, but again, they're almost preference level, right? And then functionals are going to be the quantity. Yep, that's still a great definition. Absolutely. How it do, what it do. Why it be like it is. So, first and foremost, with requirements, you will all be doing requirements in the near future as a bit of a preview of your upcoming evening lives. But these have to be full sentences. So I'm guessing I didn't stress that when we were talking about them. So when you have something like ability to search for products, we know what you're talking about, but we need to formalize it a bit more. Responsive. This is a one-word thing, right? Again, we know what it means more or less, but it's not a full requirement. So the interface must be designed as a responsive framework. For instance, if you're going for the web responsive term, right, that's where it automatically changes aspect ratio for mobile versus web or something like that. Or responsive in terms of performance, where it has to be fast, right? So you click a button and you get a very quick response. We would construct something like this in that your form shall respond in a reasonable amount of time or something of that nature, right? Or login functionality. Okay, this is probably more of a functional requirement that we have a field for serving login capabilities, right? Because this is something almost structural that we would define. But I guess here's another one, lightweight with the low system requirements. So this would tie in with performance, which is good. But we should have syntax along the lines of it, system shall support devices made within the past 10 years or something like that, right? So it's the Doom argument. Can it run Doom? It's lightweight, right? No orange or blue logo. It's a good quantifier here. So we can't have any orange and blue. Makes sense, but again, we need to make it a formal sentence. And I keep saying the word shall, and it sounds very weird, very old Englishy. That's one of the formal words that should be a requirement. The system shall do this. We're basically formally specifying with technical grammar X will happen, or X needs to happen, right? Payment apparatus, i.e. form for inputting credit card info or PayPal, etc. Right? So again, good concepts here. We just need to turn them into a technical sentence, a technical English sentence. So the system shall support payments from credit card, PayPal, Venmo, etc. Right? So these are all definitely good first attempts. We would refine them into something more concrete. This might be something that you do at a brainstorming session, honestly. So I definitely want to say good attempts. Next time we do requirements, we'll have more of a guideline of how they should actually look. But good effort overall so far. You don't care about section 2s because that's the other group. So what's going to be coming up in your near future? So I started grading the homework, so you should be getting grades hopefully by early next week. Obviously, it's a bigger homework assignment, so it's going to take more effort to grade them. And after that, you will be getting your next assignment. It will probably be rated to requirements and use cases, just as another preview. So be aware that that is forthcoming. So start thinking about what your term projects will and will not be doing. Think about the different types of interactions you will have with them, right? What are the situations in which they'll be executing? So again, we're taking this from the SE level, not strictly the implementation level. And then since we are in October, we are marching closer to that lovely halfway point. So we'll probably start getting more information about the midpoint where we have our kind of initial presentation to everybody else. So you'll get more information on that very, very shortly. So today, what we're going to cover is the different types, are the different types of UML diagrams. UML is the Unified Modeling Language. If anybody has heard of this before, please let me know in the chat. This is a formal model syntax. And what I mean by that is that we have a suite of models that are applicable to software engineering. And they're going to have different purposes, different meanings based on what the diagram is. Each model has a particular syntax. And when I say syntax, that's how we construct this model, right? What does each line mean? What is each bubble, each box, each weird looking circle with a parenthesis looking thing around it, right? These all have meanings. And the one thing that I will say here is that I am not necessarily expecting you to be experts in how to create these models. I want you to understand how to create them, though, at least at a high level. And the reason why I say this is that if you are creating these models with a formal tool, the models have to have that syntax. Otherwise, the tool will not work. So like if I'm writing a class diagram, and I'm assuming that you had that in your Java class, for instance, you can take that class diagram and automatically generate code or automatically generate Java docs or something like that, right? For that to work, your model has to be perfect for that tool. Whereas if you're making these models for an internal review or internal meeting, you don't necessarily have to be perfect with your line placement as long as you and everybody else on your team are speaking the same language in terms of the model. Right, so you will have a little bit of flexibility with how you create these models. I didn't give you one specific tool to use, right? I said use draw.io, use Visio, use Paint, whatever you can to draw these things. That's the links in the Blackboard course information page. Mainly, those are my expectations. Now, if you give me like scribbles that don't look like anything, obviously you're gonna get graded down, but it should be as close as possible to the correct syntax. And then one other thing with these diagrams that I want to caveat for you all so that we have kind of a common understanding. If you go the systems analyst route or business analyst, if you maybe don't necessarily go straight development, but you go project management or you go, one of the other roles on a team, these models will be probably very important for you. If you're a developer, there is a good chance that not only will you not want to use these models, but you will not enjoy using them. Um, so let me clarify that too, because you're going to get that it's super important in this class to do these models. Any future software engineering classes will say this is super important to learn and understand how to do. And then you're going to go into industry, and there's a good chance you never make one of these ever, which is fun to show the disconnect between academics and industry, honestly. UML is becoming more commonplace, but it's still not the norm at a lot of corporations. So models tell us about the system, it tells us about interactions, it tells us about who is using the system, it tells us about the different states. These are nice graphical models. Does anybody know or want to guess, and again, this is an open question, why I'm saying that not everybody in industry really wants to use these things? So what are some of the well, not problems, but issues with going to do requirements and then making models and then doing your programming? Why do a lot of places maybe skip the models, in your opinion? Open question to you all. Anybody have any guesses, or I'll start dropping emotes in the chat. Nobody wants an oldster like me dropping emotes that don't necessarily mean what he thinks they do. They're annoying to make, time and effort repetitive. Yeah, these are two very good guesses. And honestly, not even guesses, they are pretty accurate. Things are almost never end up like the model, difficult to make changes. So for the three of you that answered, have you ever made these models before? Because these are pretty close to what people say when they actually have to do them. Yes, I apologize. Yes, in 162. Okay, good. I'm gonna guess you didn't do all of the models in 162 though. We have a lot of different types here. So they are annoying to make. Yes, they are repetitive. Yes, 163, cool. So we have lots of various backgrounds. Missed it, GV student died on me. Yes, so basically these are going to be models that basically take what you said in your requirements and restate them. So they are technically repetitive. There is a lot of time and effort that goes into making these models, into refining them, verifying them, making sure that they are correct. So there's a lot of effort in making these things, and that's kind of what a lot of places will say is that the effort is better used elsewhere, right? More effort in testing, more effort in documentation or coding. So just be aware, this is one of those things that may get cut out depending on where you're at. However, there is a very useful reason why we actually do this. So let me pop ahead a few slides here. So here's a couple of examples. Here we have a use case diagram. Here we have an interaction diagram. I'll talk about these more momentarily, but basically here you're seeing who interacts with which activity. Here you're seeing a sequence of events happening, right? Here's a state diagram where we see the different states of the system as it moves through its path of execution, or how components get put together. Everything is extremely high level, right? We don't have detailed implementation information here. We have images, we have pictures, a nice graphical representation. And where this comes into play is that we are actually taking our requirements, whether you do it before or after, it depends on your process, but this can be used for communication. And this is communication with other people. If you give an engineer a massive requirements spec, there's a good chance that person misses something important, right? But if you give them the requirements as your reference, basically, and then you give them a series of use case diagrams, well, I know exactly which people, which systems are interacting with the various aspects of the system we're creating, right? So here's an online shopping system. We have customer, an automated service, for instance, an identity provider. These are the only three people slash systems that can touch the view items page, right? And then if we start seeing, hey, there's another, these are called actors in this particular diagram. There's another actor or there's another entity trying to view our product list. Well, there's a problem, right? Because it's very clear in our use case diagram that this actor should not be touching this system. What does that mean? We have an external threat from our environment, right? So maybe somebody's trying to hack us. We might have a model that's out of date. We might have implementation that's incorrect. So there's a lot of things that we can get out of these diagrams. But let's say that you take this diagram and you give them to your systems analyst. Maybe they're not the world's strongest coder, right? You, the developer, and your partner, the analyst, can both speak the same language using a diagram like this. And it might sound really boring or mind-numbing to make these kinds of diagrams. However, being able to very quickly talk to a feature with a customer, with an analyst, with a client, with a manager, right? Any stakeholder, something that looks like this on the screen that I've got here is very easy to discuss, obviously, right? So there is definitely a place for these models. And if you go even further down the rabbit hole, you can actually make these models work for you too, not just for communication. You can have them be part of that traceability process. You can have them be part of formal verification, where you make sure that every single state, for instance, is reachable. Or you constrain your environment so that you only handle a particular set of circumstances. And that can be model based, which is very interesting. So basically, you're making these artifacts work for you. So a little bit beyond where we're talking here. We're mainly going to be using these for documentation in this class. So why do we use these? We can visualize. So again, that's the communication aspect, very quickly discuss something. We can also use it to specify, construct, and document a system. So we can build a system from use cases where maybe then we refine them into requirements later on or vice versa. It's a great, like a brainstorming activity in a way to do some of these models, see what the sequence of events are, and then construct your system around that. Okay, so let me do a fun little, fun for me, little demo. I've got my little Pygame tile-based game right now, right? I've got a bunch of debugging text, some tiles. I can construct all of those diagrams based on what I have here, right? I have use cases for player movement, for interacting with enemies, for talking to other entities in the game, buying items, item creation, new game, save game. All of these things can be specified at a high level. And then I can either take them to requirements or I can have requirements and take them to use cases. And then make sure that everything that I've envisioned in my head actually translates into the software. So that's one of the other things too, is that what you have in your mind doesn't always make it into documentation or code. So it's kind of a nice supporting development task. So we have two high-level types of models. We have the structural models and the behavioral models. The structural types are giving you the construction of the system. So this will be the slide says the static aspects. Think of your class diagrams. Think of things that specify like the framework or how you would implement things, the actual code that you're building, things that are not changing. The behavioral is what your system is expressing. And this is dynamic, basically your different states that your system will be going through, your different interactions, your different activities, and how they will happen over time. Right? So what is your system actually doing versus how you build it? And we have a whole plethora of models for each of these. I keep talking about this system. System, 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 system. Does anybody want to take a stab at what a system is considered from a software engineering perspective? So what comprises a system? What are we thinking? Hmm. Old man Fredericks is making us talk today. Hardware code, etc. Yeah, absolutely. So if we skip to the next slide, we see hardware code and other. Good answer. Maybe the overall process that goes on. Yep. So the interesting thing is that a system can be bounded where you choose it to be. So in this particular figure, we see code, hardware, other. We might have the system boundary be also comprise the environment if we want. It just depends on how you're constructing things. In this particular view here, code is a component, the hardware is a component. Other could be like modules that you bring in. It could be any external resources, dependencies, humans if you have users. So it just depends on what you want to have be contained in your particular project, your system. You also have to deal with the environment, and users is listed here. This could be other people that maybe might be using your system that you don't specify in here. Excuse me. Um, Humans that are very difficult to quantify. One of the hardest things to do in software development is anticipate what people are going to do. So they can throw a wrench in your plans. You have to try and account for them. Other systems are going to be a part of it. So if you have a network-based application, you may be impacted by other software running, right? Or people reaching out to your system. I say people, I mean like external APIs trying to get data from you that you're pushing information to them. So how do you interact with other systems in the real world? We also have the just physical world that exists. So let's say you build an application and you're hosting it out of your home on a desktop under your desk and your power goes out. Well, the physical world has impacted your project, right? The power is out. You forgot to set up a battery backup. And now you're failing all your requirements because your uptime is now garbage, right? Or you design a vehicle algorithm to automatically do that adaptive cruise control. Well, it starts snowing, your camera gets obscured, and now you don't know how to calculate distance from the next car. We have to deal with the physical world as well. And this tends to be something that we try to represent in our requirements and our diagrams to the best of our ability. However, we don't always account for everything. And where all of our models are going to come into play here, we're trying to add the capability to handle some of these things. And then the last bit that I didn't talk about in this figure here, we also have interfaces. So how does our system interface with the environment? So what kind of framework do we have to talk to users? Or do we have a RESTful API or some kind of a queryable system for other software hardware to talk to us? How do we handle the physical world? Do we have sensors? Do we have robotic arms to manipulate things? Right? How do we touch the physical world? An interface is going to define that, and we actually have interfaces in our diagrams to handle this as well. So here's where we can kind of start to get towards more detail. And as a reminder, the question, where do we describe our requirements? That's going to be in your software requirement specification. Again, massive diagram. And we're going to expand on that in these UML models. All right, So here we have a breakdown of the different types of model that we have. So I mentioned we have two different categories, structural and behavioral. Again, structural is going to be the static things, the diagrams that go into specifying exactly how we construct our project. Okay, so class diagram is one. Again, I'm going to assume you're all aware of this. If you're not, we will be talking about it in a little more detail very soon. Class diagram, not limited to Java, I should mention as well. None of these are limited to Java. They don't even have to be limited to object-oriented languages. Right, so let's pick on class diagram for an example. That's where you specify your classes, right? All the attributes, all the methods, all the dependencies. Works fine for Java because everything's class-based, right? Python can be class-based. We can define object-oriented concepts in Python. You can do it in C++, C#, probably even Lisp or Rocket if you want to go down the deep end. Can we do it in C? If you have ever coded like ANSI C, so ANSI-C, the safety critical, very formally defined C language, there's no classes. You only have structs and pointers. Can we do class diagrams in that? Sure, absolutely. Structs can have attributes. We can have structs call functions. There's nothing stopping us from defining these diagrams for really any language. JavaScript, absolutely. HTML, not a programming language. It's a templating language. But we have these different types of diagrams. And again, class is giving us implementation structure. Object we'll talk about. This is where we instantiate a class diagram. Right, so take all your classes and then create examples of what each class would be instantiated as. We can talk about packages and how they interact with each other. So if we package up our class diagrams, and then we have packages of classes and how they interact with other packages. So there's a lot of things going on here. The other side, which I'm going to guess you probably haven't heard about as much, guess from my end, I'm sure some of you have heard of these, are behavioral diagrams, are dynamic diagrams. So use cases. Again, these are behaviors that the system is expressing. State machines we'll talk about. Sequence diagrams, interaction diagrams, timing diagrams. What happens at what particular time to each component, actor, system, right? It just depends on what level, what grain we're looking at the project. Are we looking at very broadly, very coarse-grained, very fine-grained? Just depends on your viewpoint. All of these diagrams give you a different slice of essentially the same thing. So to bring it back to that point I made earlier, why do we do this? There's redundancy, there's a lot of possibilities for failure because something doesn't get updated. It's all for informational purposes, and the more information we have, usually the better prepared you are. Doesn't mean that if you go back in your requirements engineering process to fix a requirement that you have to fix all your models. Absolutely. But usually it's time well spent. And if you look at some of the catastrophes that we talked about in the first days of class, if more time had been spent earlier on in the project defining stuff like this, that usually saves effort at the end. Effort being either just time spent or catastrophe or, right? All right, so let's talk about some of these different types here. We have a handful of different diagrams for structural. So we have classes. Again, we'll be going into these. Interfaces is how we specify what the particular operations are for a class, maybe any interfaces that they need to talk to other classes. We have instantiated classes, which is going to be your object diagrams. We have components, where effectively here, how are we grouping things together? How do they interconnect? Right, so if I have a component and another component, and components basically abstracting upwards, how do they talk to each other? How do they logically interface? Deployment, this is an interesting one. This is basically getting finer and finer grained. This is how we actually take our software and deploy it on hardware. Right, so these could be considered runtime models where, well, not run like they're not instantiated at runtime necessarily, but we're anticipating what, say, a class will be when it's executing. So how many resources is it taking up? How many components are active? Right? What impact is it having on a system? Then we go to the behavioral side. I'm not talking about all of them again. This is high level today. We have our use cases, which I'll be going into a little more detail soon on. And that's actually our next module is on use cases. But here we're getting the goals for what you should be doing, right? These are going to be a verb-noun representation. So if I pop over here, this is a whole use case diagram describing a particular feature or a goal or something like that. The bubbles are the use cases. So each bubble is a use case. It's going to be in a verb-noun format. So it's very straightforward, very crystal clear what's being described. View items. We know exactly what that means, right? This will be linked to a set of requirements which specify, okay, exactly how do we view items, right? What are the requirements? What are the constraints? This might be linked to other models like a class diagram where we instantiate a view items class. We have dependencies in here as well, right? So making a purchase, well, that includes information from view items because we need to be able to see everything to buy it. Or we have to have a checkout use case where if we want to make a purchase, we need that functionality. So taking some of these relationships that we may know from other classes or from earlier where we're including functionality, maybe we're extending functionality to take some base idea and add extra functionality to it. Maybe you want to generalize, so you have a generic construct and then you specialize based on particular features you want. Common animals, you have an animal, you can have a dog, a cat, a fish, clams, depends on how you want to specialize, but you have a base class and you would inherit from that. So we can capture some of these ideas at a high level in a use case diagram. We also have interactions. So how do objects interact over time, right? They can be in the form of a sequence diagram, meaning that we're looking at how information flows from component to component, or how we simply organize this mess with the collaboration diagram. So here is an interaction diagram. Again, we'll be going into more of these later on, but here we have different actors, different entities effectively. If somebody's trying to call another person, we have your phone exchange, we have a receiver, so who is the person receiving the call, and then we're going to be able to talk. It's obviously throwback to when phones plugged into the wall. But let's actually take a look at this here because it's interesting, to me at least, and I'm not going to talk about interaction diagrams anymore after this today, until we actually get into the details, obviously. But what we have here is effectively a series of responsibilities down this dotted line. So I want to make a call to one of you, and I'm going to use my big old rotary phone to do that because that's how we do it in 2020. First thing I have is an initial state where the phone's on the hook, right? So it's just sitting there. If I want to start a call, I have to take it off, right? So first thing that happens, phone goes off the hook. This links up to the phone exchange, which sends me a dial tone. So you hear that in your ear when you pick up your phone. Then you dial a number. The exchange understands what the number is and routes it. Right? I could say 20, how did they used to make calls? Like Mackinac 20 or something, and then the operator would put it into the right slot. Go way throwback. But that number gets dialed, and then a ringtone gets sent to the receiver. The receiver's phone then has to obviously ring, so it's on the hook. And then once the person picks it up, I right-clicked by accident, then we go off hook and we go back to the exchange. So what we see with a diagram like this is a sequence of events that have to happen. And not only that, but we see who's responsible at which stage of the process. And you're going to look at this and say, oh, this is BS. Obviously, I know how a phone works. Pretend you're a programmer who has to actually implement a series of if statements, right? Because this is what you get right from this. If call not started, phone has to be off the hook. If phone off the hook, send a dial tone. If dial tone sent, handle number, right? So we have a sequence of events that can happen here. It's a very simple diagram, obviously, but we can expand on this, right? Think of programming one of your term projects or developing an autonomous car, or even just making tea or coffee. What are the series of steps that goes into making perfect pot of caffeine to keep your professor going through the hour? um, so these are the kinds of things that we care about, right? Sequences of events. What objects are being slung around to which receiver, right? So this gives us a really good idea of how things are working behind the scenes. We also have state charts, activity charts, so we'll be talking about these as well soon. So here we have a state diagram example. And one of the things you may have to consider in a project is what are the states, right? So if we think of a video game, which again, sorry for using video games all the time. I enjoy talking about them. Talking about them. You start a game. So you're sitting at the loading screen. That's my state. I'm loading all my assets in. Then I go to the main menu state. I'm sitting waiting for user input, right? So we are in initial state, game not launched. We go to the loading screen where we pull in all of our assets. Then loading's done. Our event is that loading is completed. Then we go to the main menu. We sit and wait in the main menu until we get user input. Okay, well, the user might select load game. That brings us to the load game state. What are we doing there? We're pulling all of the save data off the disk, and we're parsing it and setting everything up so that the user can start their save game. Or we could go to a new game state, or we could go to the options menu, right? These are all different states that we have to handle. Do we get implementation details out of this? No. But we understand program flow, right? We understand exactly what has to happen in a particular state. And not only that, how do we transition from one to another? So if I'm sitting here in the options menu, I'm expecting user input, right? We're not just going to go back to the main menu. That would be, well, bad usability design for one, but we would violate our state machine. We also have other diagrams too, which are more for refinement. So we have our component diagrams where we have basically different components of our system, and we see how they can mesh with other components. What's a component? It's basically an abstracted package in a way. So we're seeing how information can be placed together. We have these funny little circle and half like an arc kind of thing. Here's how we're putting things together. Think of it like trains linking up, right? These are how components can talk to each other. We'll be getting into all of this fun stuff. So what I would like to do now, unless you have any questions, I'm going to do a little example here for my game, and I'm hoping that my tablet works a little bit better than it did last time. I think the streaming software doesn't like this, but pop over to my game here. Again, what I'm working on is a little fun to me type of game where we have a character moving around a randomly generated environment. Eventually, you're going to start talking to people in here as well. But thing I care about right now is map generation. I'm just in a box, right? There's no cell, there's no walls really, there's no paths to go down, there's no trees, it's just a gray, blurry mess. Well, how do I take that to a system? Well, what we have to do, see, it has my arrow here. All right, I'm gonna kind of lean down a little bit. So let me, necessarily gonna try to give you a weird view, but it's not too bad. It's looking at my camera here. All right, so I've got a use case diagram that I need to draw. All right, and what I want to do is I want to capture the high level intent of my system. All right, so let me unhide your chats here just so I can see if anybody has a question. What things do I care about when I'm starting a map generation algorithm? Well, I might be considering when a user first logs in to my game. So they can start the game, they can load a game. If I start, I'm going to have to generate all the initial states, including your first map. If I load a game, I have to pull things off the disk. And then let's say that we get to that point, I have to initialize the game state, meaning, again, what does the map look like? Are there any objects on the floor? What enemies do I see right away? When we get further into it, we'll have non-player characters that can talk to you, things of that nature, your typical, fantasy game stuff, right? But what I care about is this initial set of cases. So what do we have here other than hopefully not bad professor writing? So I want to start my game. So, wow, let's just freeze. Great start. Come on, stop drawing. Thank you. I keep clicking things. That's the problem by accident. My pen has a, I might have to just go do this in, yeah, this thing sucks. Sorry about that. Let's just go to Draw.io, because that's what I told you all to use anyway, right? Get out of here. Quick pirouettes, Draw.io. Hey, we have a conversation one. That's from my grad class. All right, let's just do this. This is so much better. All right, start game. And actually, this is a good example why a tool like this is helpful, because we can just move things around a lot easier. Start game. Load game. I don't even know why I didn't bother just doing this in the first place. Silly professor, thinking you can draw on your faux whiteboard. Initialize state. And let's generate next level. All right, we all see this okay, I think? Yeah. All right, let me zoom in a little bit so we can see this. Yeah? Yeah. All right. So here are 4 use cases that I could see being part of my initialization for my game. I'm just kind of coding willy-nilly right now, right? I don't have set formal requirements. I just have a vague notion of what I want to create. Think of it your typical term project. Okay, so if I want to load the game, this means that I have to have some way for players to save their game, meaning that I have to have some kind of a state that I'm pulling. So every time that I see what's the correct, no, I don't want to do that. This? Yeah, there we go. And this should be dotted. Can I do this? Hey, easy peasy. Now where's the text? This is going to extend. Extend. Okay. What does this mean? If I want to load the game, I have to extend whatever functionality I have to start it. Right, so I have some code in here to kick things off. Maybe when I load it, I need to yank from that. And then add on my extra feature, which is pulling data off the disk. Again, I don't have firm requirements for what this means, but I know it's an activity I have to do. This will also feature in with my activity diagrams later on when I'm going to figure out where this goes in my program flow. Also kind of where you start to see where this is an extra activity that you have to go through, which may not necessarily be as exciting as you thought it was. All right, so over here, I need to include something. So can we draw, please? Hey, there we go. All right, so now if I want to initialize the state of my game, I might either be starting from scratch, because it's the first time, or I might have like level 2. Level 2's enemies are harder. Level 2 has more health drops because it's so harder, or something. So to go to the next level, I need to have whatever code's in here, and then I'll probably seed it with a different random number value or a different modifier to make it harder. It's still the same code, but it's not the basis, right? And generate next level also may have other activities in there, like generating, random map code. So here are my 4 initial kind of ham-fisted use cases. I can draw what we call a boundary, and 2 back. Perfect. I like this much better already than what I was trying to do earlier. Apologies to section 2. So what is a boundary? This is where interaction starts and stops for these use cases. By drawing a boundary, we can figure out which actors we're going to put in here. And what is an actor? An actor is going to be a person, or it's going to be another system that will touch one of these use cases in some way. All right, so if I want to, let's see, start, and if I want to play the game, I, the person, so let's call me, yeah, not that. Player character, PC, right? I will be the one initiating the start of the game. So let's draw a line to you. I also have the option to load a game. Please. There we go. So I know that the person in front of the keyboard will be doing one of these two activities, right? Does the player initialize the state? Does the player generate the next level? No, that's going to be something automated. So I don't have any interaction with these two states, meaning that in my requirements, the user will never have any interaction here. We're never going to have any input into what the level generation is. We're never going to have anything that a person should be doing with these internal things. And if we ever see that, there is a verification failure later on, a test failure, right? We have lots of things we can do with this. You could tweak this to add like a random seed. I know a lot of you have probably played like Minecraft or Binding of Isaac or Terraria or any of those games where you can put a seed in. Well, that would be a connection to initialized state then if we did something like that. Okay, so we have the player character. Let's also add a engine, right? So game engine. You are a actor. Depending on your preference for UML, automated systems can either be a box like this, or they can be another stick figure. It just depends on what your preference is and honestly, which version of UML you use. So this is still an external entity to this particular diagram, but we can see, again, what the interactions are here. So the game engine is going to be the one initializing the state, right? So some internal logic is in charge of generating everything. We can also have it be part, yeah, that's not what I want to drag. There we go. Part of the next level generation, right? Because we need to increment the level, and we need to update our dictionaries of all of our objects, so on and so forth. So the game engine needs some interface here. What else do we have? We may also have a map generator, right? So map generator. And since this is a roguelike game, we might be doing a BSP type of thing where we recursively carve out dungeon rooms and connect them. Get your standard NetHack type of dungeon going. Could do cellular automata, something a little more organic. Go with Dwarf Fortress model where it's a whole world being generated. It just depends. We don't care at this point. We just know there is some entity that will be handling that. What are they connected to? Well, let's generate the level. Generate the level could be generating level 1, so we don't necessarily have to have the map generator initialize the state. One thing to consider, this is all arguable too, right? So this is how I envision this particular use case diagram. I ask you all to do the same thing. I can guarantee I'm trying to get 30 separate use case diagrams describing the exact same intent. That's fine. That's just how we all envision workflows. This is my mental model. Yours may be different. So we have something like this. What we're going to talk about next time is how to formally define these models, how to take these use cases and specify them a little bit more. So let's take initialized state, for instance. With this use case, we also will have something called a use case description, which turns it into an object. Give it an ID, who's responsible for it, which actors touch it, what requirements is it linked to. Again, goes to that notion of traceability. And then how will this feature in like an activity flow? What are the different states it can go through? So we start seeing how all these can kind of link together as we go. What else are we going to talk about? Oh, these use cases will also form a part of your activity diagrams as well. So I guess interaction diagram, don't have a good picture of that. Me, a quick Google image search, activity diagram. So I don't have a good picture. So something that looks kind of like this, where we have actions or activities and we have branching paths. Your use cases will actually kind of slot right into this. And then you start seeing program flow and things of that nature. So it all kind of comes back full circle. Does anybody have any questions from today? Hopefully it made sense. It's a lot of me talking, so if you have any questions, if you zoned out and you want more detail, please feel free to ask. But next time we'll be getting deeper into UML or use case diagrams. Sorry. Everybody good otherwise? Cool beans. Radio silence in chat, so I assume either you're all bored out of your minds, there is a delay, or we are all good. So, I hope you all have a wonderful weekend. I will see you all very soon next time, and have a great weekend. I think I said that already, but oh, we gotta get some awesome outro music. Sorry. Gotta have it, right? I had human music in here earlier. There we go. Bye, everybody. Have a great weekend.